Brendan, who is going to tell us about classification of small 2D CFTs.
Great. So thanks so much to the organizers for giving me the opportunity to speak here today. I'd like to tell you about two papers. One was written with Sunil Mukhi sometime last year, and the second I posted to the archive a little bit earlier this year. And let me just say from the outset that this second paper was submitted in coordination with two other groups. One is a familiar group of physicists, and the other is a group of two mathematicians. I'll try and say in a little more detail where I overlapped with these two groups. But in the first part of the talk, which will be mostly focused on bosonic CFTs, essentially most of the things I'll have to tell you are largely independent from what they did. And then in the second talk, when I turn to, in the second part of the talk, when I turn to fermionic CFTs, that's when I'll comment more on the relation to this work. So in this talk, I want to advocate for a fairly general program for classifying 2D CFTs, and then illustrate how it can be carried out in a special case, which will ultimately lead to this table, which I'll explain in more detail as we go through the talk. So since I'm in a Bootstrap conference, I can omit much of the motivation that I'd otherwise be giving. But because there's a bit of a sociological divide between 2 dimensions and higher dimensions, let me just remind of some of the killer apps that are somewhat unique to 2 dimensions. So one is, of course, that we can make contact with string theory through the world sheet. Another potential motivation, if you're a particular kind of person, is that structures that are closely related to 2-dimensional CFTs often arise as key actors in various dramas of pure mathematics. And some buzzwords here are maybe moonshine, Langlands, so on and so forth. But even if you insist on being a higher dimensional person, 2D CFT techniques can help you there as well, because supersymmetric quantum field theories in higher dimensions often have various protected sectors which organize themselves into structures related to 2-dimensional conformal field theory, like chiral algebras. Okay, and just as the applications are perhaps a little bit different in 2 dimensions, so too are the techniques that are commonly used. So in greater than 2 dimensions, I think we often think about, we often study the 4-point function, and we bootstrap theories by imposing crossing symmetry. In 2 dimensions, there's another observable which is very natural to consider, which is the genus 1 partition function. I'll remind you its definition. And here, the analog of crossing invariance is modular invariance. And so a strategy for studying 2D CFT is to either try really hard to milk the constraints of modular invariance, or to even just write down solutions to the modular crossing equations and, in some sense, try to classify them. Although these two problems might appear very different, in 2 dimensions they actually are mathematically essentially identical due to this happy fact that the moduli space of the 4-punctured sphere is essentially the same as the moduli space of T2. And so you can, in fact, recast this left-hand side into the language of modular forms, if you'd like. Okay, so at this point, I want to make perhaps an obvious comment. And the comment is just that partition functions are not the same thing as 2-dimensional conformal field theories. They're not equivalent in any sense. And there's at least 2 reasons for this. So one is the fact that there simply exist isospectral theories. In other words, there exist pairs of theories Is this too light? Right. So there exist isospectral theories. There exist pairs of theories which cannot be distinguished by their T2 partition functions. Is this better? Perhaps the most famous example of this are the two heterotic string theories in 10 dimensions, which are supersymmetric, whose world sheets are isospectral. So you wouldn't be able to tell these two theories apart if you just were a person who studied torus partition functions. Yep.
Are there any known examples where the central charges are not integers in this happens?
Of course, I can always tensor the Ising model to these two examples, and they're still isospectral. And actually, but less stupidly, there's many examples in this table of theories with fractional central charge, which are isospectral. So it's a completely generic phenomenon of two-dimensional conformal field theory, yes. The second point is that there exist partition functions that don't correspond to any theory. Even though they look completely healthy, they're modular invariant, they're positive, everything you like about them is true, but no corresponding CFT. So an example of this is there's this somewhat well-known C equals 24 chiral CFT called the monster CFT. And if you take its partition function, you can always add any positive integer n you'd like to it. Constants are modular invariant. And yet we know that there are only finitely many theories which have this as their partition function. In fact, there are 71 theories which have a partition function of this form. So for these two reasons, studying just modular invariance is insufficient. And so really the goal of this talk will be to try to work in a setting in which it is possible to say more and really genuinely take up the problem of classifying two-dimensional conformal field theories.
One might think that the second point is not just that they exist, but they're generic, that most partition functions that are modular invariant do not correspond to CFTs. And for instance, there's the reasons, kind of conjectural constraint from topological modular form on meromorphic theories that will rule out most candidate partition functions.
Absolutely. I mean, there's infinitely many values. Infinitely many of these partition functions don't correspond to CFTs already. So yeah, I totally agree. Great. So part of this game will be to try to find a question which, try to find the right question that strikes the appropriate balance between tractability, but hopefully at the same time it should admit a non-trivial answer. So how should we organize the landscape of CFTs? We can't just sort of go out and try to solve the full problem all at once. And one immediate thought is to try to organize by the central charge. This is completely natural from the point of the renormalization group flow, because the question that we often ask in quantum field theory is, given a UV CFT, which is perturbed by relevant operators, what is the fate of the theory at low energies? What is the IR CFT? And this is, of course, a hard problem in general, as we just learned from the previous talk. But there are constraints. For example, there's Zamolodchikov's C theorem. And so if you'd like, if you had an answer to the question, what are all conformal field theories with central charge less than CUV, then you'd have a sort of a priori list of possibilities for what this IR theory could be. So it'd be great if we could have some kind of result like this. Okay, so let's see how far we can get in that program of classifying CFTs in order of increasing central charge. So you start off strong. As we learned in the previous talk, there's the theories with C less than 1 are classified, and there are discretely many minimal models, starting with the Ising model, which accumulate at central charge 1. Okay, so this is part of the reason why flows between minimal models are under comparatively better control than flows between generic conformal field theories. At c equals 1, something somewhat drastic happens. There's infinitely many theories. In fact, a continuous conformal manifold opens up. And I don't believe it's proven in any sense that this is the full moduli space of theories, but it's a conjecture that any C equals 1 theory is either a free boson theory, or in other words, a sigma model into the circle, or it's a Z2 orbifold thereof, so a sigma model into the interval, or it's one of 3 isolated theories, which can be obtained by going to the self-T-dual radius, which has an enhanced SU2 times SU2 symmetry, and essentially gauging exceptional finite subgroups of that enhanced SU2. So this is the conjecture. And I claim that if you tried to go any farther, you know as close to little as possible about what the landscape of theories looks like. For example, even if we try to probe just the neighborhood around C equals 1 to the right, I claim we don't know even the coarsest features of that. For example, is there a gap between C equals 1 and the next central charge, which is realized by a CFT? Is there an accumulation point from the right as there is from the left? Is there a continuum? Somehow none of these questions have straightforward answers or even expectations. So we should, this is probably too hard for now. So we should refine our question instead. And to introduce that.
I'm surprised you say not even expectations, because from examples, what is the expectation?
Yeah, no expectations from examples. The issue is examples can only get you around here. And you might try to play some game where you combine known ingredients to get to find examples of CFTs that sort of accumulate to C equals 1, but I know of no game that you can succeed at. So to introduce this refined question, let me remind you that what makes two-dimensional conformal field theory so tractable is that they always have infinite dimensional symmetry algebras called chiral algebras. Essentially, these consist of the operators of the theory, which are holomorphic. And so this is always non-empty. There's always something in here, essentially because the stress tensor lives in there and generates a Virasoro algebra. Another kind of universal entry that you expect to appear in the chiral algebra is if you're in a situation where you have a continuous global symmetry, you have an expectation from Noether's theorem that there be conserved spin 1 currents. And these will generate something called a current algebra, or WZW algebra. So here X is A, B, C, D, E, F, G. A for SU2, B for SON, D also for SON, and so on and so forth. R is the rank, and K is this level, which is related to the anomalies of the global symmetry. Okay, good. So these will be important later. And whenever you have a big symmetry, or any symmetry really, you should try to organize your observables in terms of its representations. And so in particular, you can take the CFT Hilbert space and decompose it into representations of the left and right moving chiral algebra. So the right moving chiral algebra is simply the set of the space of anti-holomorphic operators. Sorry? Oh, yes, good. Or U1. And okay, in favorable circumstances, the number of representations which appear in this decomposition of the Hilbert space is finite. And in particular, when it's finite, we refer to this as a rational conformal field theory. Good. So the goal will be to organize the space of theories simultaneously by C and P, this tuple of numbers. And one reason that this is a very natural thing to do is that there's a conjecture, which is substantiated from all known data, that the number of theories with fixed C and P is finite. Okay, so if you like, just organizing by C led to a big continuum of theories, and so somehow P is like a regulator, so that it turns our question finite. Great. And so let me christen this problem with a name. Just for the purposes of this talk, we'll refer to the problem of classifying all conformal field theories with central charge less than or equal to some fixed central charge, and with a number of primary operators, which is less than or equal to some fixed number. That's called the CP classification problem. And that's the problem we're going to be concerned with. So the immediate question is, what are reasonable values for C star and P star? How far can we sort of reasonably hope to get? And so let's start with C star. Reasonable value for C star. And to get a sense for this, I'm going to restrict to the special case of P equals 1 for now. And let's see how high we can get. So when P equals 1, the only primary operator is the identity. And in fact, I can even discard the entire right-moving sector and think of it as a chiral CFT in its own right. So I'll often colloquially refer to CFTs with only one primary operator as being chiral CFTs. Okay, so it's known on grounds of modularity that the central charge has to be a multiple of 8. So it turns out there's a unique theory, E8 at level 1, one of these current algebras, when C equals 8. At C equals 16, you get the two world sheets of the two heterotic string theories. When C is 24, it turns out that there are 71 theories. Of these, 24 of them can be obtained essentially as free bosons. Which are constructed from so-called even unimodular lattices. And if you like, the rest of these 71, in some sense, emanate from one of these free boson theories, namely the free boson theory which is constructed from the Leach lattice, which is this, I think, familiar lattice in this community which solves the sphere packing problem in 24 dimensions. And these other ones can be obtained by essentially gauging finite symmetries of that Leach theory. Okay, so it looks like we're in good shape, but I claim that this is the sort of strict cutoff for what one could explicitly do, at least. And the reason is that if you estimate the number of theories that live here, you find that there are more than 1 billion. And the reason for that is that you can estimate just the number of free boson theories using lattice techniques. There's this formula from the mathematics community called the Siegel-Minkowski-Smith mass formula. And it tells you that the free boson theories alone comprise 1 million. And they're not even expected to be the majority of theories. So I don't think you can expect an explicit table like the one on the right if you push beyond this c equals 24 ceiling. So with that, I will, without apology, restrict to c star equals 24 from now on. OK. Well, what about p star? So to get a sense for this, let me actually refine the question one step further by introducing the so-called modular tensor category associated to a 2D CFT. Actually, let me not describe it in terms of category theory, because I don't think that would be received well. But instead, this is really equivalent to a 3D TQFT. And this 3D TQFT, you should think, is the sort of bulk 3D theory on which the chiral algebra can end as a boundary. Okay, so the most familiar example of this maybe is when you take V to be one of these WZW models or current algebras, in which case the bulk 3D TQFT is none other than Chern-Simons theory based off of the same Lie algebra and the same level. What did I want to say next? Right. So, but crucially, this isn't the only chiral algebra which can be the boundary of Chern-Simons theory. There's actually infinitely many others. Okay. So somehow, maybe one other thing I should say is, why is this a refinement of P? And the reason is that there's a correspondence between sort of topological line operators in the bulk and representations of the chiral algebra on the boundary. So in other words, the bulk 3D TQFT witnesses the number of primary operators through the number of topological line operators it has. So number of primaries of V goes over to number of topological lines. Okay. And so one of the reasons I prefer to carry around this extra baggage of this full 3D TQFT with me is that it leads to a kind of conceptual clarification of what the defining data of a 2D RCFT is. So in particular, I claim that for any 2D RCFT, you can sort of draw a three-dimensional picture that describes it. So what you do is you place the left-moving chiral algebra on one boundary of this bulk 3D TQFT. You place the other one, the right-moving chiral algebra on the other boundary. And in the bulk, you have the 3D TQFT. And perhaps in the middle, you have the liberty to insert a topological surface operator. So if you'd like, this topological surface operator, I erased it, but is essentially giving you the data of this matrix Mij, which glued together the left and right moving representations of the chiral algebra. Yes?
Just to clarify the logic, especially for the Bootstrap audience, the assumption of the modular tensor category seems to go a little bit beyond just the usual crossing axioms. In particular, let's say just at the level of the chiral algebra, you just think about the OPE, but here there's braiding. I mean, we believe it's true for rational CFT, but logically, that's more than just the usual OPE axioms.
Well, I'm appealing to sort of rigorous theorems from the vertex operator algebra community. So if you believe that the the notion of a vertex operator algebra is kind of the axiomatization of OPE and crossing symmetry, then if you impose certain technical assumptions, like what would equivalently be known to physicists as rationality, then it's proven that somehow the representation category of a chiral algebra is a modular tensor category. So I am perhaps making a slight, I think the physicist notion of a rational CFT is not fully well-defined, but if you sort of make a small leap that the thing that physicists call RCFTs are the same thing as what mathematicians call rational VOAs, then I think this is all kosher.
Yeah, I guess I'm not totally, I'm not familiar with the precise theorem that asserts the relation between the modular tensor category and vertex algebras. I thought the braiding essentially implies modular invariance in some sense. That's kind of can be understood in an elementary way, but it seems to me that there's some kind of gap in just going from the associative the OPE to that, but maybe you're telling me that.
It's of course not the associativity of the OP alone. It's also, there's the technical assumptions are C2 cofinite, rational. So you make various assumptions, and then
yeah, I'm just wondering if there's some fine prints in these assumptions that goes a little bit beyond the usual axioms that bootstrappers work with.
Of course, rationality is key, right? It's a statement about the category of representation. So for a non-rational theory, this would not be true.
That's certainly true, but that's kind of built into the definition of the modular tensor category in some sense. There's some finiteness, but also the relation between braiding and modular invariance only works if you have finitely many topological lines. But
yeah, I'm certainly assuming.
That's certainly true, but
I'm certainly assuming finitely many representations of the chiral algebra. I'm making this additional so-called C2 cofiniteness assumption, but that essentially is needed to ensure convergence of the characters. I'm happy to write out all the technical assumptions maybe afterwards. But I think when the dust settles, you'll basically find that the situation I'm describing is precisely that of RCFT with P primary operators. I think. But yeah, for the purposes of this talk, if you think that the MTC needs to be an additional assumption, then you can safely make that, yeah. Any other questions? Good. So as I was saying, this picture really leads to a conceptual clarification for what the defining data of an RCFT is. So you, of course, have to pick a chiral algebra V. That's the first step. And then you have to pick one of these surface operators, which is essentially the same thing as a modular invariant, this matrix Mij. But sort of crucially, what this picture shows is that the second part doesn't really depend on any of the details of this chiral algebra V, but rather it only depends on its bulk TQFT, which is which is a very coarse invariant of the chiral algebra. So it depends only on TQFT. And I'll explain why that is important in a minute. So from this discussion, what we learn is, remember, we're trying to ascertain what is a reasonable value of P star. And so what we learn is that we can, the problem of classifying theories with at most P star primary operators is at least as hard, in fact, way, way, way harder than the problem of classifying TQFTs with at most P star topological lines. So TQFTs with P star lines. Okay, and for this result, we can appeal to the mathematics literature, which has carried this process out up through about p star equals 5. But life is too short to classify all the CFTs, so I'm going to stick to p star equals 4. Good. So, and then the next point to make is that when the number of primary operators is this small, it just turns out that most TQFTs essentially have only one choice of this surface operator. In other words, for most of these theories, the only modular invariant Mij you can pick is essentially the identity matrix. And so all of the complexity of this classification problem that we're trying to address really boils down to enumerating the possibilities for this chiral algebra V. And somehow, once you've enumerated all of these options, it's a very straightforward algorithm to glue them together into full non-chiral RCFTs. So I won't discuss this problem any further, and the rest of the talk will be dedicated to enumerating chiral algebras by with these properties. And just as maybe a bit of nomenclature, I'm going to call the genus of V the tuple consisting of its central charge and its bulk 3D TQFT. So that's the genus. So we're gonna classify chiral algebras by genus.
I just want to make a comment here. I guess the term topological lines used a bit loosely here, referring to these Verlinde lines. Since if you just talk about the more general topological lines, they don't have to be described by the modular tensor categories. It can just be described by some fusion category without braiding. So
absolutely. I mean, the topological lines I'm referring to are in the bulk TQFT, but of course those are related to the Verlinde lines on the boundary. But yes, I'm not trying to make any statements about the full symmetry category of these CFTs. I'm just sort of saying that if you take a rational CFT and you pick its maximal chiral algebra, then that'll be an MTC, and I'm sort of organizing by the MTC of that maximal chiral algebra.
I guess I kind of never understood logically the property of these Verlinde lines. How do they really follow from just the standard kind of OPE type assumptions of for rational conformal field theory? It seems, like the claim of the relation to the modular tensor categories, that there seems to be a big leap that just intuitively I don't quite understand whether it's possible to really derive it from just based on the usual OPE axioms, naive OPE axioms.
Yeah, I'd like to understand better what level of proof you'd want. Yeah, I don't know that I have anything particularly insightful to say about that. I mean, the statement that I'm aware of is that, as you say, the symmetry category is a fusion category, and the Verlinde lines are obtained by taking this MTC, which has more structure, and just forgetting some of the structure in it.
So I also have a confusion, because to me it seems like what do we have here? We have a finite number of primaries. So when we are going to start constructing correlation functions, we are going to be basically operating with the finite dimensional sums of various conformal blocks. So I don't see any room for any sort of infinity or divergence to occur in all these expressions. So the only question is going to become, can we actually define single-valued correlation functions on any Riemann surface? So why do we need some extra conditions? I don't know, C2 confinedness, whatever. Why do we need extra conditions?
Leonardo might want to answer that.
Yeah.
Sure. I think C2 cofiniteness is a technical assumption that is literally cooked up to make, for example, the T2 partition functions converge. It's a necessary condition.
For what? But we're already assuming there's a finite number of fields. So what is the room for divergence in the T2 partition function? It's going to be a finite sum of characters of this chiral algebra. So
But the characters themselves might, in principle, diverge before you've imposed this. So C2 cofiniteness is a condition on the chiral algebra.
Yeah.
And it's meant to ensure that the characters, so I agree, like once you take the sums, assuming the characters are finite, then the full T2 partition function is finite. But the characters themselves might diverge is the issue.
So this C2 cofiniteness guarantees finiteness of characters.
Yes. And yeah, as Leonardo said, there's this expectation that C2 cofinite is a necessary condition for having a finite number of modules. But as far as I know, they haven't proved this rigorously yet, so they add it as an extra assumption.
So you could, in principle, have chiral algebras with an infinite number of modules, but is Mij 0 for most of them, and so they don't appear in your partition function?
For me, I see what you're saying. No. All the chiral algebras that I will consider have finitely many modules, for sure.
Because of your C2 cofiniteness.
Because of, I'm assuming rationality of the chiral algebra. I actually don't know if it's possible to have a chiral algebra with infinitely many representations, which nonetheless admits a CFT in which only finitely many of them appear. I suspect that's impossible, but I think I would have to commit stronger to that statement offline, maybe.
Can you also comment on this claim? I mean, usually people say that, okay, in the old days, Cyberg and Moore classified like set down some rules for rational CFTs. Are you just sticking to that old framework, or are you going beyond that?
I'm very much working within the Moore Cyberg framework. I don't think, well, maybe back in the day they were very optimistic that one could produce a full classification of rational conformal field theories, but I mean, it's a very difficult problem as.
But did they make this assumption, C2 cofiniteness, whatever, in their paper? There's nothing like that.
Yeah, yeah. Maybe Leonardo can.
But why do you have to go? It's a concrete question.
Yeah, I think, I mean, I don't know, so I haven't sort of fully compared Moore Cyberg to the math papers, but I think probably it's implicit there. Yeah, I mean, that's maybe all I can say at this level. Do you have anything you want to add?
Any rational theory that anybody in this audience will recognize as rational has a C2 cofinite VOA. I promise that.
Yeah, I should say, so I'm trying not to like make any provocative claims, but I think anything that anybody's ever encountered that has had the word rational tied to it will be covered by what I'm considering. So, okay. So by the way, I didn't mention this yet, but here are the TQFTs with at most 4 line operators. I tried wherever possible to express them in terms of Chern-Simons theory. Turns out that most of them have a pretty clean description, just as straight up Chern-Simons theory, and other ones are maybe closely related. Good. And now, so if you look at this table here, this tells you the list of all theories which have, if we stick to the left of here, the list of all theories which have central charge less than or equal to 8, and at most 4 primary operators. And if you look here, if you sort of organize theories by their bulk 3D TQFT, for each TQFT there's at most 1 theory, with the exception being this one for which there's no chiral algebra. So I want to explain to you how to, and by the way, that situation changes as you go to higher and higher central charges. So for example, yeah, I mean, there's hundreds over here. So you should imagine that lower central charges are more tractable, so I'm going to start with C less than or equal to 8 and explain the derivation of this. How much time do I have? Okay. So here's the only place in my talk where I will appeal to the modular bootstrap. And I'll sort of use it in a comparatively pathetic way, as you'll see. So for each genus CC, which has C less than or equal to 8, and at most 4 primary operators, there is a unique function which could serve as the partition function, or the vacuum character, let me say. So I'll say, which could serve as this character of the vacuum. Okay, so somehow, if you fix the TQFT and you tell me I'm only allowed to consider theories with central charge less than or equal to 8, then there's at most one spectrum that you could possibly find. And actually, I'm not going to use almost any of the spectrum except for one piece of it, which is the number of spin 1 currents. So in particular, what this result tells you is that within each genus, there's a fixed dimension of the global symmetry algebra. So in other words, if we expand it like this, then this number is the dimension of whatever the global symmetry group is of your chiral algebra. Okay, and so that's already a huge constraint. And there are a few other constraints that we will use. So the first is that the rank of this global symmetry algebra should be less than or equal to the central charge. What's the intuition behind this? Well, you should think that if you pick a carton of your global symmetry group, those U1 currents can be bosonized, and each contribute central charge 1 to the overall central charge. And so the central charge contributed by the carton should not exceed the total central charge of the theory. And so we obtain a constraint like this. Good. So let me just so these currents, the operators in this weight 1 subspace, they generate one of these current algebras that I wrote for you earlier. So if you'd like, we could write it like this. So we have 2 constraints already. One is on the dimension of these G's, and the other is on its rank. The sort of final thing that we have to figure out how to constrain is the levels here of the current algebra. And that should follow from something like this. So the currents themselves will contribute a Sugawara central charge to the theory, something like this. And again, the central charge that's contributed just by the currents should not exceed the total central charge of the theory. Oh, that's important. And so we get a bound like this, which can be used to constrain the levels. Okay, so let me just give you one example of how you can use these 3 constraints in conjunction to prove uniqueness of theories in a particular genus.
I usually think that this is not the only place where you use margin invariance. I think the modular tensor category in some sense already uses margin invariance in some way. Because usually the way I think about it is the modular tensor category basically classifies the possible crossing kernels of the W algebra conformal blocks. But just for the crossing at the sphere level, usually I think you only need a pentagon identity. There you also have this braiding beta hexagon identity, and that's tied to the modular invariance.
Yeah, I agree that the modular tensor category brings about the conditions for me. Yeah, the modular tensor category structure existing tells me that the characters transform in some finite representation of SL2Z. And the only thing I'm saying is that the only place that I'm like literally using the characters is to extract this one puny coefficient from them, which tells me the number of currents. That's the only sort of claim I was trying to make. I agree somehow the consistency of this entire picture hinges strongly on this MTC structure existing, but for this purpose.
Yeah, I just have the feeling that the MTC uses the modular invariance in a very non-trivial way, that the bootstrapper that only thinks about crossing on the low P level would not have thought of. Yeah.
Yeah, I think I agree with that, yeah. By the way, is this pen still readable? So let's consider any chiral algebra which has central charge 7 and which can be the boundary of E7 at level 1 Chern-Simons theory. So if you crank the modular bootstrap machinery, what you learn is that the unique function takes this form. And so we learn that whatever chiral algebra lives in this genus, it must have a dimension 133 global symmetry group. And also, its rank by that constraint should be, that constraint should be less than or equal to 7. And it turns out that the only Lie algebra with dimension 133 and rank less than or equal to 7 is none other than E7 itself. Thank you. Appreciate that. So it remains only to constrain the levels. And I claim that the only choice of level here, which renders this inequality true, is level 1. So if I number these, this is 1, 2, 3. So in the first step, I used 1 and 2. And this last step, I used 3. And from there, it's essentially a few lines to conclude that E7 at level 1 is, which I guess one could have expected, is the unique theory in this genus. But of course, this proves that there's no others, which we didn't know a priori. OK, so I claim that if you run these sorts of arguments through for all the other TQFTs in that table, then you'll be able to produce essentially that first column of theories with C less than or equal to 8. However, these techniques become kind of difficult to use as you go up in central charge. For example, over here you can see that there's hundreds of theories sometimes with a particular TQFT. And so that should suggest to you that you're not going to have the analog of this lemma as you crank up the central charge. You're not going to have just a unique possible spectrum. And so we need sort of new techniques so that we don't have to analyze, so we don't have to do a lot of hard work analyzing hundreds of different possible spectra. So for this, let me remind you of the definition of a coset. It's fairly general, although it's perhaps most familiar in the context of WZW models. So let's say you have some chiral algebra.
Sorry,
Yeah.
I have a naive question. You have Ising there, I think?
Yeah, right there.
What's the TQFT that you started with?
The TQFT could be called the Ising TQFT, but it's sort of isomorphic to that of B8 at level 1, or SO17, 17 at level 1.
And that Chern-Simons theory.
That Chern-Simons theory supports the Ising model on its boundary.
OK, I did not know that.
Yeah. There's a lot of kind of accidental isomorphisms of TQFTs, of course, because many different Chern-Simons theories are dual to one another. And OK, this is an example of an isomorphism between a Chern-Simons type theory and this Ising category.
Thanks.
So cosets are a sort of less familiar cousin of orbifolds in that they're a very efficient machine for producing new theories from old ones. So given some chiral algebra V and a subalgebra, you can fairly generically produce a new chiral algebra, which I'll call V mod W, which schematically consists of the operators in V, which have regular OPEs with the operators in W. So it's sort of like the analog of a centralizer in a group. It's all the things inside of V that commute with W, essentially. And maybe a familiar example is that if you take V to be SU2 level 1 times SU2 level k, you take the coset of a diagonally embedded SU2, which it turns out implies that its level should be at k plus 1, then you recover a kind of nice nice coset description of the minimal models, the A-series minimal models. Okay, and so here's a fact, which I won't substantiate for you here, but I'm happy to give some intuition behind afterwards, or maybe offline, is the following. So fix some W in some genus. Let's say that we want to take up the problem of enumerating theories in a dual genus. So enumerate theories in some genus where the TQFT is the orientation reversal of the one up here. So for example, it turns out that A1 at level 1, Chern-Simons theory, is the orientation reversal of E7 at level 1. Well, here's the claim. Any W twiddle in this genus, in this dual genus, takes the form V mod iota W, where here, this is a P equals 1 theory, or a chiral CFT, with central charge C plus C twiddle. This is this fixed seed theory, W, that was given to us by God up here, fix some W. In practice, we're going to take W to be one of these guys over here. And this iota runs over embeddings, all possible embeddings of W into V. Because in principle, different embeddings can give rise to different cosets. So in a sense, I'm telling you that enumerating theories in this dual genus, once you have this fixed seed theory, is essentially algorithmic. It reduces to a problem of enumerating cosets of this very specific type. And there are 3 reasons why this is tractable. Oh, I'm so happy I didn't erase this. So the first reason is that all the possible choices of V have been classified. Those are these guys over here. Also, candidate W's are known. That's what we did in this first step, classifying theories with C less than or equal to 8 over here. The wildcard here is how easy it is, or how difficult it is, to enumerate embeddings of the W's into the V's. And I claim that it turns out to be very computable, at least in this situation, because if you'll see here, most of the W's are essentially just current algebras. And that leads to a simplification. Sorry, I'm moving around so much. Because W's are current algebras, their embeddings are easy. So in other words, your intuition should be that figuring out all the ways that W embeds into V, if W is a current algebra, essentially reduces to a problem of ordinary Lie algebra embeddings. And that's a very classical problem for which there are many tools available. Okay, how am I doing on time? Oh, good. A conspiracy.
Well, for each TQFT, it looks like there's a unique central charge in the third column. Is that some artificial
Sorry.
consequence of the fact that it's...
The TQFT fixes the central charge modulo 8. So in fact, there's infinitely many central charges which are compatible with a given. For example, for the trivial TQFT, the central charge is 0 mod 8, and so you have chiral CFTs at central charge 8, 16, 24, 32, and so on and so forth. And likewise, for, say, the Ising category, you can have CFTs of central charge 1/2, 8 plus 1/2, 16 plus 1/2, and so on.
So for a current algebra, it's not just the Sugawara central charge?
Sorry. There's two different things which I've written using very similar notation. There's the current algebra, and then there's the bulk 3D TQFT. And those are different. So the current algebra, it is what it is. It's just some chiral algebra. But the corresponding Chern-Simons theory need not only support its corresponding current algebra on the boundary. It can actually support infinitely many different chiral algebras on its boundary.
Okay, I think I'm following now.
Yeah, okay. Thanks for the question. So, okay, so let's do the E7, just a quick example. We'll do the E7 level 1 TQFT one more time, except we'll increment the central charge by 8. So you anticipated this. Okay, so what do we have to do? We have to enumerate cosets of the form, of this form, excuse me, A1 at level 1. So why A1 at level 1? And that's because it turns out that the orientation reversal of E7 at level 1 is A1 at level 1. So our fixed seed algebra W, we can just take that corresponding current algebra. Here, the only two possibilities I mentioned are E8 squared and this other sort of SO32 theory. And okay, so this problem essentially just reduces to figuring out ways that SU2 can embed into E8 times E8 or SO32, which is a very straightforward problem. And it turns out that you get two theories. And one of them, so you can always do this. E8 at level 1 has a trivial TQFT. So you can always stack it on top of E7 at level 1, what you had at central charge 7, and get another sort of trivial theory. So that coset arises by taking V to be E8 squared. And the other one, okay, you'll just have to believe me, that it's some kind of funny theory where you take SO28 and SU2 at level 1, and then you introduce a few more operators by extending the theory. Okay, so in total you find two theories in this genus, and that's this two right here. There are many, but it turns out, so you can't just use any embedding. You have to use an embedding that's compatible with the fact that all these levels are at level 1. So at a technical level, what you're looking for is embeddings of SU2, which have embedding index 1. So that's a sort of extra condition you have to add. And it turns out there's one for each. Yeah.
What is the logic for constructing a TQFT associated with coset embedding here?
Good. Yeah. So, okay, there are more general statements, but for the purposes of this discussion, the TQFT of a coset of a thing with trivial TQFT. So maybe I should write this. So in general, in general, the TQFT of V coset W is some anion condensation of TQFT of V times TQFT of W. This is a theorem. And okay, so in this case, our V is has trivial TQFT, so this goes away. So in general, you expect it to be an anion condensation of the TQFT of W, but it just turns out that most of these W's don't have any non-trivial anion condensations. So, sorry, this should be conjugate.
So this language smells a bit like the gauge WZ model. Is that where it comes from, or is it independent of that?
I think gauged WZW models are certainly an example of theories which flow to the corresponding cosets.
Yeah, I'm just saying, usually intuitively, at least that's the only way I know how to understand that the coset construction gives rise to, let's say, MTC, among other things. Because to know the vertex algebra itself is a very trivial thing. I mean, that just amounts to the vacuum module of CFT. It's obvious that that has closed OP and so forth, but it's much more than that. So.
Okay, good, thank you. So, yeah, there is a leap here for people who are pedantic, which is that this theorem assumes that the coset V mod W is rational. This is actually an open problem in the math community, proving that the coset of two rational VOAs is again rational. But for the purposes of this talk, we actually don't need to rely on that conjecture, because we can explicitly compute what this coset is and just observe that it's rational all of the time. So sort of by inspection, it works. Okay. And okay, maybe this table deserves some more comment. So I guess I didn't say this, but each entry here is sort of the number of theories, with central charge C being in between this range and with the associated modular tensor category. So here you reproduce, for example, the 71 theories I wrote over there, and in general you get hundreds more as you go up here. So this is almost a complete table except for these frowny faces where I gave up. So, but I should say that a consequence of the work of Moller and Hon, which I referred to at the beginning of this talk, is that these frowny faces are actually completed now. And I'll explain why now, as I shift my attention to fermionic theories. So this is I outlined a fairly general program that you could certainly attempt to push higher for classifying bosonic CFTs. It turns out that the problem of classifying bosonic CFTs and classifying fermionic CFTs, well, this turns out to essentially be a special case of the former, and I want to explain why. So the main idea is going to be that fermionic CFTs and bosonic CFTs are related by bosonization and fermionization dualities, which are, in some sense, invertible. For the purposes of what I have to tell you, I'm actually not going to use the sort of standard bosonization and fermionization mappings, but rather some kind of versions of them which, instead of operating at the level of the full CFT, rather operate on the level of the chiral algebra. So let's say you have a, this is going to be bosonization. Let's say you have a fermionic CFT. In the NS sector, it has some chiral algebra. And I'm always assuming unitarity and spin statistics and things like that. So you can decompose this theory into operators with integer conformal dimension and operators with half integral conformal dimension. So integer spin and half integer spin. And okay, so Bosonization is very trivial. It just amounts to taking the fermionic theory and returning its bosonic subalgebra. But I also sort of want to keep track also of this V1 piece, which in terms of the bosonic subalgebra is interpreted as one of its representations. So if you'd like, bosonization takes a fermionic chiral algebra in the NS sector, gives you back a bosonic chiral algebra along with a distinguished choice of one of its representations. And sort of trivially, this is invertible. You can always recreate the fermionic chiral algebra that you started with. So the question is, what bosonic algebras, if you didn't know in advance that this bosonic algebra that you were given came from the fermionization of a fermionic chiral algebra, how would you know what you're allowed to fermionize? The only conditions are the following. So the conformal dimension of this should be in a half integer. And its fusion rule it should sort of square to the vacuum, if you'd like, for its fusion rule. And then I claim that given any bosonic chiral algebra which has such a representation, which satisfies these properties, you can always fermionize it and produce a fermionic chiral algebra. So example, take Ising, add to it its representation of spin 1/2, and you get the chiral fermion. For my purposes, I'm going to be, again, using vertex operator algebras as my axioms, and so this would be a vertex operator superalgebra, even though it's not supersymmetric, but the mathematicians like to call Z2 graded things super. And I'm only going to be working at the level of the chiral algebra, so I will politely refuse to define for you what a full fermionic CFT is. Okay, so let's think about what happens here in a special case. So for my special case, I want to consider the case that V and S is a so-called chiral fermionic theory. So this is kind of the analog of this situation for bosonic theories. We called a bosonic theory a chiral CFT if its only primary operator was the identity operator. And likewise, we'll call a fermionic CFT chiral if its only primary is the identity operator in the NS sector. And an example is free chiral fermions, and free chiral fermions are examples of chiral fermionic CFTs.
Well, it sounds like the vertex algebra you're referring to here just in NS sector, but usually the R sectors need to play a role. That comes in somehow?
That comes in. That's what's known as a twisted module, a -1 of the F twisted module. So in VOA, in the VOA world, they not only consider ordinary representations, but representations which are twisted by finite symmetries. And it turns out that for them, twisting by -1 of the F gives you the Ramon sector.
But usually by demanding the existence of Ramon sector and its certain properties, I would assume that they put some constraints on this the vertex algebra itself. I mean, when you say you define, let's say, the fermionic CFT through the vertex algebra, how that is somehow put in implicitly?
I think they go the other way. So I think they define vertex operator superalgebras in the NS sector, and then they show that the Ramon sector exists, essentially, is my understanding. Yeah, I don't think you would find a nice NS sector chiral algebra of the kinds that I'm restricting to, which again basically means rational, that didn't have an accompanying consistent remote
Yeah,
sector.
I guess I'm wondering what part of the, what kind of assumption you put on NS sector vertex algebra that implies this existence of R sector? A way, if there's an intuitive way to understand that.
Yeah, good question. It's going to again be like, I'm just going to have to say rational, C2 cofinite, these kinds of things. But yeah, I'd be happy to parse through those assumptions in more detail with you. Good. So we're restricting to fermionic theories with one primary operator in the NS sector. And OK, what should you get when you bosonize these theories? So claim is that the TQ of T of V0 of the bosonization is spin 2C at level 1, where C is the central charge. You always get this. And OK, I'm using different notation, but the spin guys over here are the B and the D Chern-Simons theories. So they're like this and this. So in other words, yeah, so in particular, the number of topological line operators in spin 2C at level 1 is always less than or equal to 4. So the upshot is that if you take any chiral fermionic CFT with central charge less than or equal to 24, and you bosonize it in this somewhat contrived sense, then you'll get a bosonic chiral algebra, which must arise in this table somewhere. And if you go the other way around, what this means is that I should, in principle, be able to construct all possible chiral fermionic CFTs by starting with the data of that table and figuring out all the consistent ways of fermionizing them into fermionic theories. And so you can do this. And this leads to the classification of chiral fermionic CFTs with central charge less than 23. And why less than 23? Well, it's because this frowny face is, well, these three frowny faces are 24, 23 and a half, and 23, and I wasn't able to do them. But Hohn and Moeller did this up through central charge 24, so they filled in these three of these frowny faces at least. And the physics group, actually I should put these on equal footing. Math. Physics group went through up through C less than or equal to 16, plus they had a very nice discussion about the relationship to non-supersymmetric heterotic string theory. So central charge 16 chiral fermionic CFTs are precisely the sort of ingredients that define a consistent world sheet for a 10-dimensional heterotic string theory. And so in particular, this kind of closes a somewhat tiny gap in the literature where it was unknown whether all the fermionic CFTs that had been written down at C equals 16 were truly complete and exhaustive. Okay. I'm basically done. Some future directions. Let me just take 2 minutes if that's okay. Okay, I guess one future direction would take too much time to describe, so let me just describe the other, which I think is a cute problem. So I started off the talk very pessimistic about the prospects of classifying chiral CFTs above central charge 24, because there are just simply so many of them. However, there are some more structural statements that you could attempt to make. And in particular, one hope is that there's a following theorem. So any two chiral CFTs with same central charge are related by gauging. What's the evidence in support of this? There's two pieces of evidence. One, it happens to be true for all free boson theories. So all chiral free boson theories are related by gauging some sequence of ZP symmetries. And it turns out that at the first central charge where we witness non-free boson theories, it's true there as well. So at c equals 24, actually I think I commented on this, everything sort of goes through the leech. Everything can get to leech by gauging and then get anywhere else by gauging again. So V leech. Okay, so I think this would be a sort of interesting problem to try to tackle, which imposes some structure on the otherwise chaotic landscape of high central charge chiral CFTs. Okay, and with that, I'll conclude.
So you mentioned at some point that you could push this program. So could you like explain, apart from this future direction, like what would be the goal of pushing this program? Because you already have a ton of theories, so you're going to get yet more. So what's?
Yeah, so I won't do it. But well, okay. So I mean, there's various motivations you might have. More data is always good. So since the beginning of time, when dinosaurs roamed the earth, there were conjectures about, of the form, all rational CFTs should be the following, and somehow they all seem open, and it's unclear what their status is. So I think truly getting more data where more complete set of data like this could sort of give you some expectations for what those conjectures could look like. I mean, there's lots of other ones, I think. So one maybe contrived other application is, for example, there's various toy models of holography that feature low central charge CFTs and ensemble averaging and things like this. And some of these chiral CFTs actually make an appearance in those examples. I think, organizing theories by genus, each genus provides a very natural ensemble of CFTs. And actually, one of the things I'm thinking about on the side is whether or not these fit into a sort of toy holographic story like that. Yeah, what else? So, okay, since you asked, actually, another natural thing to do is, so maybe this more justifies why we did this. So as far as these fermionic CFTs go, you get a lot of theories this way, which end up being related to pure mathematics. So for bosonic chiral CFTs, I already mentioned there's this monster CFT, which has this exceptional finite group symmetry. It turns out if you look at the literal, so this is the first chiral CFT without any continuous global symmetries. And already the first bosonic chiral CFT without any continuous global symmetries has a very interesting finite symmetry group. What about for chiral fermionic theories? There, at c equals 12, which again is sort of the first, I can explain in more detail what I mean by non-trivial, but first non-trivial chiral fermionic CFT, it happens to have an n equals 1 supersymmetry structure. And the automorphisms of this theory, which respect n=1 supersymmetry, form a finite group. And again, this is an exceptional sporadic group. Now we have an infinite tower, not an infinite, excuse me, a tower of chiral CFTs up through central charge 24, which, if they do admit supersymmetry, should have finite supersymmetry preserving automorphism groups. And I think it's a really interesting question to ask what kinds of finite groups you get, whether there's any connections to pure mathematics like the moonshine stories, which involve these two theories as key actors. And so,
Any other questions?
So it's commonly believed that on the conformal manifold of supersymmetric sigma model with K3 target space, the rational points are dense. Do you have some hope to classify all of them, say the MTC of all these theories?
that's a great question. Yeah, that's a very interesting question. I don't have any ideas for how to do that, but it's a natural place to look. Regarding more general Calabi-Yaos, my understanding was that the denseness of the rational points had been, I'll just say evidence had been produced against that. And in fact, it's only either a finite number or sparse number of isolated points that for which a generic Calabi-Yau becomes rational. Maybe K3 is different.
Isn't this a no-go based on speculative conjecture? This complex multiplication thing of Gukov and Vafa? I mean,
that supports the opposite conclusion, right? Oh, you're saying if you apply...
No, what's the other evidence for the statement that on the Calabi-Yau, for the Calabi-Yau threefold, say, supersymmetry model, that the number of rational points are finite, let's say?
Let's see, did people study conformal perturbation theory around these Gepner points and find some result that was suggestive of this? Yeah, I should ask Nathan again.
It sounds difficult to rule it out just based on conformal perturbation theory. I mean, how is it qualitatively different from the K3 case?
Less supersymmetry, maybe. Yeah, it's a good question. I should double check before I make any strong claims.
So if you restrict to lower C, like C less than 8 or even less, is there any hope that you can go down in P and try to understand all these rational theories below C equals 2, say, or something?
Yeah, good question. So a kind of intermediate result that I relied on heavily is the classification of modular tensor categories or of 3D TQFTs. And without a result like that being known for, so you just mean any number of primary operators, C less than, yeah, that is, I think, challenging, but never say never. I don't think the techniques that I've used would be particularly helpful for that, sadly.
I mean, it was not clear to me from your talk if you can actually make an algorithm and just run a computer to continue to produce more and more, and then it's just too slow, or if you have to be smart at every point and do it slightly different.
Well, you have to be smart at some points, and these frowny faces were points at which I wasn't smart enough. In the case that a conspiracy happens and these low central charge theories happen to be pure kern algebras, it essentially becomes algorithmic because the cosets that you have to take are very straightforward. In other cases, I don't think, for example, here's a seed theory. It involves E6 at level 1 and one of the minimal models. So in order to figure out these theories, you'd have to figure out all cosets by this thing. And I don't know of any general techniques which tell you all the ways to embed a minimal model chiral algebra into some other random chiral algebra. So presumably this one requires some amount of intelligence and thoughtfulness. And yeah, I think, so you could continue listing out TQFTs, but I think very quickly your luck sort of runs out in the sense that this conspiracy that most of these theories ended up being pure kern algebras stops happening very quickly. So in a sense, it was it's a very happy circumstance that the MTCs and these theories turn out the way that they did.
I also have like a naive question. So when you at the start of your talk by talking about C less than 1 theories,
Yeah.
but there, for each center charge, there is a series of theories with a different set of operators, different partition functions, so the AD classification.
Yep.
So in that case, so there is actually some extra work to be done, and I'm not sure how it was done in the old days, but using this MTC approach that you are using, do you have some simple way of understanding this AD classification?
Yes. So I commented on this briefly in passing. So those modular invariants, so yeah, the different ADEs are basically different choices of modular invariants, which in this 3D TQFT picture corresponds to different choices of this surface operator.
Yeah.
Those have a very concrete mathematical definition in terms of algebra objects in this MTC. And okay, so you can, the reason that like classifying infinite families of modular invariants is difficult is just the infinity, but here you have a very finite problem to tackle, and it turns out that for most of these theories, the only modular invariant is the trivial one. For some of them, they have other ones, but they're also easy to enumerate. So I would say that the problem of enumerating modular invariants for this special class of theories is solved. I did sweep something under the rug, which was that I was assuming that the CFTs have the same left and right moving chiral algebra. That can also be relaxed very straightforwardly, and so I think, yeah, I think when the MTC is small, when P is very small, this game of gluing together left and right is very easy, and it's the main difficulty lies in figuring out all the choices of chiral algebra.
Okay, thank you.
Yep.
Well, let's first of all thank Brandon.
Okay, just one small minor comment. So as you know, we